For thousands of years, humanity looked up at the night sky and saw nothing more than flickering points of light. Without telescopes, without knowledge of physics, without any sense of distance. To the human eye, stars appeared almost identical. Small, bright points suspended in the sky, moving according to fixed patterns. Stars inspired myths, religions, and legends in virtually every civilization. In Mesopotamia, they were seen as signs from the gods. In ancient Egypt, they were associated with the afterlife. And in Greece, they became the foundation of mythology, where entire constellations were heroes of ancient tales. For ancient peoples, stars were guides for travel, agricultural calendars, and sometimes tools for predicting the future. But despite thousands of years of observation, the true nature of the universe remained a mystery. No one knew what stars really were, how far away they were, or whether anything existed beyond Earth. The breakthrough came only in the 20th century. The development of telescopes, physics, and mathematics made it possible to understand that stars are not points of light, but enormous spheres of plasma, similar to our sun. They differ in mass, temperature, color, and lifespan. Some live for billions of years. Others explode as supernovae after just a few million. Space probes and orbital telescopes revealed that the universe is not static. It is dynamic, violent, and full of extreme phenomena. We observe stars being born in clouds of gas, the deaths of massive suns, collisions between galaxies, and black holes that bend time and space. This discovery completely changed how we perceive reality. Earth turned out not to occupy any privileged position, and our galaxy is just one of hundreds of billions. An avalanche of discoveries in the 21st century recent years have brought a true avalanche of discoveries, greater than all previous decades combined. Technological progress has made data collected by telescopes and probes more precise than ever before. Today, we are not only observing the cosmos, but beginning to analyze it at a chemical and physical level. We can study the atmospheres of planets orbiting other stars, detect specific molecules, and determine surface temperatures of alien worlds. We analyze matter older than Earth itself, originating from asteroids and comets. We create maps of the invisible part of the universe, showing where mass exists that we cannot see, but whose presence is revealed by gravity. These are not theories or speculations. They are hard data that force scientists to revise existing cosmological models. James Webb Space Telescope, a cosmic revolution. In 2021, a telescope was launched into space that would change the way we look at the universe. The James Webb Space Telescope did not replace Hubble. It complemented it by observing regions Hubble could not. Webb observes the universe in infrared light. This is crucial, because light from very distant objects is stretched by the expansion of the universe and shifted into this range. Thanks to this, Webb can see objects that were previously completely invisible. One of the first shocks was images of galaxies that formed just a few 100 million years after the Big Bang. These galaxies are surprisingly large and well organized, suggesting that structure formation in the universe happened faster than previously thought. The light from these objects traveled more than 13 billion years to reach us. This means that when we look at them, we see the universe almost at the moment of its birth. But Webb is not just about galaxies, atmospheres of alien planets. James Webb has, for the first time, enabled detailed chemical analysis of exoplanet atmospheres. During a planet's transit across its star, the telescope records how light passes through the planet's atmosphere. From this, scientists can determine which molecules are present. In this way, water vapor, carbon dioxide, methane, and other chemical compounds have been detected. By themselves, they are not proof of life, but they are key components of biological processes known from Earth. This is the first time in history that we can not only infer the existence of planets, but actually study their physical and chemical properties. Webb has also discovered galaxies that appear too massive and too mature for their age. This challenges existing cosmological models and suggests that the universe may have evolved faster than we assumed. Exoplanets, new worlds. Just 3 decades ago, we did not know of a single planet beyond the solar system. The first discoveries in the 1990s were a sensation. Today, they are routine. We now know of thousands of exoplanets, with more discovered almost every month. These planets are incredibly diverse. There are worlds larger than Jupiter, orbiting closer to their star than Mercury. There are planets smaller than Earth, nearly devoid of atmospheres. There are icy worlds and others where temperatures reach thousands of degrees. Some planets experience extreme weather, hurricane-force winds, clouds of metal vapor, and even rainfall of molten iron. Others are tidally locked, always facing their star with one side, resulting in eternal day on one hemisphere and eternal night on the other. The habitable zone. Particular interest surrounds planets located in the so-called habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. The TRAPPIST-1 system is one of the most fascinating discoveries of recent years. 7 rocky planets orbit a small, cool star. Several of them have sizes and temperatures similar to Earth. We do not know whether life exists there, but for the first time in history, we have specific observational targets that can be studied over the coming decades. The origins of the solar system, matter older than Earth. To understand how planets form, we must go back to the beginnings of the solar system. In 2023, a capsule containing samples from the asteroid Bennu returned to Earth, delivered by the OSIRIS-REx mission. These samples are more than 4.5 billion years old, older than any rock on Earth, and untouched by geological processes such as tectonics or erosion. They contain carbon, minerals, and organic compounds, exactly the ingredients that form the basis of life's chemistry. Their analysis helps us understand what materials were available in the young solar system and whether similar processes could occur in other planetary systems. Bennu is just one object, but its significance is enormous. Thanks to such samples, we can better understand whether life is a rare exception or a natural product of cosmic evolution. When we look at the samples brought back from Bennu, one thing stands out: the life we know did not begin on Earth. Its foundations formed earlier, in interstellar space, long before our planet was born. Atoms of carbon, oxygen, nitrogen, and hydrogen are not a local invention of Earth. They are products of the deaths of earlier stars. Every atom in our body was once part of a supernova. This discovery changes our perspective. Life no longer appears as a miraculous exception, but as a potential consequence of the laws of physics and chemistry. If similar conditions arise in other planetary systems, if the same ingredients are present throughout the cosmos, then the question is no longer whether life exists elsewhere, but how often. In laboratories on Earth, scientists analyze cosmic dust, simulate conditions in molecular clouds, and discover that complex organic molecules can form spontaneously in a vacuum at low temperatures under radiation. Amino acids, the building blocks of proteins, have already been found in meteorites that fell to Earth. This means that the chemistry of life does not require a planet or an ocean. It can begin in space and only later find favorable conditions to develop on the surface of a young world. The universe as a laboratory. For most of human history, the cosmos was seen as a backdrop, distant, unchanging, and passive. Today we know the opposite is true. The universe is a gigantic laboratory where chemical and physical reactions constantly occur on scales impossible to reproduce on Earth. In star-forming nebulae, new suns and planets are born. Near black holes, matter reaches energies unattainable in Earth-based accelerators. In collisions of neutron stars, elements heavier than iron, gold, platinum, uranium are created. Each of these phenomena leaves an imprint on the structure of the universe. With increasingly sensitive instruments, we can read these traces. Gravitational wave detectors like LIGO and Virgo have allowed us for the first time to hear the universe, recording ripples in space-time caused by collisions of massive objects. This is an entirely new sense added to optical, radio, and X-ray astronomy. Thanks to this, we know that black holes are not rare. They are common elements of galaxies, and their mergers are among the most energetic events in the universe. Dark matter. The invisible structure of reality. One of the greatest discoveries of the 20th century was realizing that most matter in the universe is invisible. Stars, planets, dust, and gas, everything we can see, make up only a few % of the cosmos. The rest is dark matter and dark energy. Dark matter neither emits nor reflects light, but reveals its existence through gravity. It holds galaxies together, affects their rotation, and shapes the large-scale structure of the universe. Without it, galaxies would fall apart and stars would scatter into space. Although we do not know exactly what dark matter is, we can map its distribution. By observing how its gravity bends light from distant objects, a phenomenon known as gravitational lensing, we create maps of the universe's invisible skeleton. These maps show that galaxies are not randomly distributed. They form enormous filaments and voids, resembling a cosmic web. On the largest scales, the universe looks like a three-dimensional spiderweb, with galaxies clustered at the intersections of invisible threads. Dark energy and the fate of the universe. If dark matter is responsible for the structure of the universe, dark energy determines its future. At the end of the 20th century, astronomers discovered that the expansion of the universe is not slowing down, as expected, but accelerating. Something is acting against gravity, pushing space apart faster and faster. That something is dark energy, the most mysterious component of the cosmos. We do not know what it is or where it comes from, but it makes up about 70% of the universe's total energy. It will determine whether the cosmos expands forever or meets a different fate. One hypothesis describes the so-called Big Rip, in which expansion becomes so rapid that it tears apart galaxies, stars, planets, and eventually even atoms. Other scenarios involve eternal cold expansion leading to cosmic heat death. Each of these scenarios sounds abstract and distant, but they are based on data collected here and now. By analyzing supernova light, the structure of the cosmic microwave background, and the distribution of galaxies, we try to understand the fate of everything that exists. The microwave echo of creation. One of the most important pieces of evidence for the Big Bang theory is the cosmic microwave background radiation. This faint, nearly uniform radiation comes to us from every direction and is a remnant from when the universe was just 380,000 years old. At that time, temperatures dropped enough for atoms to form stably for the first time, allowing light to travel freely through space. This radiation is like a cosmic photograph of the infant universe. By analyzing its tiny fluctuations, scientists can extract information about matter density, the age of the cosmos, and even processes that occurred at its very beginning. Satellites like WMAP and Planck delivered data with unprecedented precision. From this data, we know the universe is about 13.8 billion years old and remarkably uniform, with small irregularities that became the seeds of future galaxies. Inflation, the moment that changed everything. One of the most revolutionary ideas in cosmology is inflation theory. It proposes that a fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion, growing unimaginably large in a very short time. Inflation explains why the universe is so uniform and flat on large scales. It also explains the origin of tiny fluctuations that gave rise to cosmic structures. Although inflation remains a theory, more and more observations indirectly support it. The search for characteristic inflationary signals in the cosmic microwave background continues, and confirming them would be one of the greatest discoveries in the history of science. Are we alone? This question, asked for thousands of years, is finally becoming more than philosophical. Programs searching for extraterrestrial life, such as SETI, analyze radio signals from space, looking for patterns that might indicate a technological civilization. So far, no definitive evidence has been found, but the scale of the search is only just beginning. At the same time, astronomy is shifting its focus from civilizations to biology. Instead of radio signals, we increasingly search for biosignatures, chemical signs of life in exoplanet atmospheres. Oxygen, ozone, and methane in specific proportions may indicate biological processes. James Webb and future telescopes will be increasingly suited to such observations. Perhaps the first evidence of extraterrestrial life will not be a radio signal, but the spectrum of a distant planet's atmosphere. Mars, a former second Earth. Among all objects in the solar system, Mars remains the most intriguing. Today it is a cold, dry desert, but billions of years ago it was a world with rivers, lakes, and perhaps even oceans. Rovers like Curiosity and Perseverance have provided evidence that Mars once had conditions favorable to life. Scientists have found minerals formed in the presence of water, organic molecules, and sedimentary structures resembling ancient lake beds. Perseverance is collecting samples that are planned to be returned to Earth in the future. Their analysis may answer one of science's most important questions. Did life arise independently more than once in the solar system? If the answer is yes, the consequences will be enormous. It would mean that life is a common phenomenon in the universe. Icy moons. Oceans beneath the surface Mars is not the only place where we search for life. Increasing attention is being paid to the icy moons of gas giants. Europa, a moon of Jupiter, hides a global ocean of liquid water beneath its icy crust. Enceladus, a moon of Saturn, ejects geysers containing water, salts, and organic compounds into space. These worlds have everything we consider essential for life: water, energy, and organic chemistry. Moreover, their oceans may be stable for billions of years, far longer than life-friendly conditions on Mars. Future missions will study these moons with unprecedented precision. The answer to the question of extraterrestrial life may lie not among distant stars, but in our own cosmic neighborhood. Humans in space, back to the moon and beyond. Alongside scientific research, a new era of crewed exploration is developing. The Artemis program aims to return humans to the moon, this time to stay. The moon is meant to become a testing ground for technologies needed for missions to Mars. Building bases, using local resources, and long-term stays beyond Earth are challenges that must be solved. Mars remains the ultimate goal. The first crewed mission to the Red Planet would be one of the most significant events in human history, a first step toward becoming a multiplanetary species. A new perspective. Each of these discoveries, from the chemistry of cosmic dust to the structure of the entire universe, leads to one fundamental shift in thinking. We are not the center. We are not an exception. We are part of a process that began billions of years ago and encompasses the entire cosmos. Stars are born and die. Planets form from dust. Chemistry leads to biology. Biology to consciousness. And consciousness begins to ask questions about its own origins. When we look at the night sky, we no longer see just flickering points of light. We see history, our own history, written in the stars. And perhaps, somewhere out there, someone else is looking at their version of the night sky, asking the same question. Are we alone? And that is why this journey does not end. It is only just beginning. If you want to keep exploring space, science, and the mysteries of the universe, subscribe to the channel and join the journey. Because the most fascinating questions are still ahead of us.